Sri ADICHUNCHANAGIRI Mahasamsthanam, His Holiness Jagadguru Sri Nirmalananda Swamiji, Professor C.V. Prasad, former scientist, Vikram Sarabhai Center, Vice Chancellor Madhya University, Dr. Putraju, CEO Sri ADICHUNCHANAGIRI Shikshana Trust, Dr. M.S. Ramegowda, Principal of SAC College, Dr. B.K. Lokesh, faculty members of the college, students of the college, as well as the delegates to this international seminar. First of all, I would like to thank the management of this Shikshana Trust for giving me this opportunity to be part of this seminar and also say a few words about the topics that are being covered in this particular seminar. So many advances have taken place all over the world in both basic and applied physics. It is almost impossible really to be a master of all of them in a short time. So therefore, seminars of this kind, where experts come and talk to the delegates, are very essential, so that immediately one can have contact with the experts, communicate with the experts, clear the doubts and gather the important aspects of any field. So therefore, activities of this kind, that is seminars, workshops, conferences, are very essential for any higher institution such as a college or university. I am sure this management will take note of it and organize more such activities in the coming days. So one can broadly divide. I am going to talk about what are the recent developments in various branches of physics in a nutshell, not really in a detailed manner. So one can broadly divide the developments into three groups. In the first category, we have developments extremely small scales of mass, small length and small time scales. Next we have advances in the other extreme, very large masses, very large distances, very large time scales. So these are matters of astrophysics and cosmology. So then finally we have the intermediate level advances which are taking place in the intermediate levels of mass, length and time, such as what we are familiar with in everyday life. Okay? So at the smaller scale, I will begin with the smaller scale, what are the developments, then go to the other developments in organized fashion. At the smaller scale, we have what is known as the standard model of elementary particles. So it is also known as quantum chromodynamics. So it deals with the most fundamental particles and their interactions with one another. In this model, we have two kinds of particles, namely quarks and leptons. So these quarks are the matter particles, and then we have what are called the force mediators, which are bosons. The matter particles are represented by quarks and leptons. These are the most fundamental ones. All other particles are made up of quarks and antiquarks. So there are 6 quarks and 6 leptons identified. These are the most basic elements. So they are further grouped into 3 families or generations. In the first generation we have up and down quarks. These are just names. Up means not up and down. Up quark and down quarks. Along with electron and its corresponding neutrino. So these 4 form what is called the first family. Then these are the most abundant particles in nature. So then we have another family having charm quark, stage quark, muon particles, mu neutrino. The second family. The third family we have the top quark, bottom quark, tau meson and tau neutrino. So these have been discovered, and for discovery of such particles, Nobel Prizes have been given in the past. So commonly see particles like protons, neutrons, which we are made of. We are made of protons, neutrons, electrons most of the time. All the elementary particles, they are not stable. They are very unstable. So these are the ones stable. So they consist of up quark and down quark, that is the electrons and neutrinos. So interaction between quarks and leptons are mediated by particles called vector bosons. These are somewhat technical terms for those people who are not familiar with some of the particles, but at least you will get to know more about that in the seminar if you participate. So the vector boson, this vector boson, they have got spin 1. Okay, that is why vector boson. So these are, for example, examples of gluons. These are particles which mediate strong interaction. Then we have W particles. These are mediators of weak interaction. So three fundamental interactions are there in quantum gluon acids: strong interaction, weak interaction, electrolytic interactions. Okay. Then we have the Z particle and the photons. So these are what are called the vector bosons. So interaction is described by theories. They are called gauge theories, which incorporate what is known as the local gauge invariance, the local phase invariance. These are high technical terms. I'm just going to summarize. Probably you will hear more about them in the seminar. So local gauge invariance is a requirement for coupling the particles with the gluons and the vector bosons. So mathematical simplicity or mathematical consistency requires what is known as the renormalizability, that is vector bosons that are proposed, that is W boson, photon and other particles, gluon, they are supposed to be massless for mathematical consistency, or what is technically known as renormalizability. So the question arises therefore as to how one can account for their masses. Their masses, we know that they got mass, W particle they got mass, Z particle they got mass, gluon they got mass. Okay? Photon is one which has no mass. So how to account for these masses? That is a big puzzle. Okay? So the mechanism, therefore, a mechanism for generating mass was proposed in 1964 by Peter Higgs. So that is why it is named the particle which was discovered later according to his proposal is called Higgs boson. So you see a photograph this thing there. This one. The last person there, that is Peter Higgs on the banner. Last person on the Peter Higgs. So Higgs proposed, he was not the alone person, there were several other persons at the same time who proposed the mechanisms and developed it further so that mathematical consistency is achieved. So whenever a physical theory is represented mathematically, it should have consistency and give you finite results. So these were achieved in the subsequent years, and they proposed what is called universal scalar field, okay, to account for the masses, and this scalar field is supposed to have non-zero vacuum expectation value. What happens if I go into more detail? The particles will be fluctuating, they will be having zero vacuum expectation value. Then they will not give you masses. So this Higgs particle is supposed to have a non-zero vacuum expectation value in nature. So then therefore, because it couples with other particles, it generates mass. So that is what is called the Higgs mechanism for producing masses. The excitations or quanta of such a scalar field are called Higgs particles or Higgs bosons. So some scientists, they dub this particle God particles. Okay, just to highlight that these are very important particles. And this is an important particle because it is able to generate masses for so many other elementary particles. So it's very fundamental. So God created this field, which is very universal, and therefore they call it God particle, but technically it's called Higgs boson. So people began to look for that from 1970s onward, people began to look for it. So any theory which is proposed has to be verified experimentally. The proofs, however beautiful the theory might be, unless experiments show that it is correct, it will be rejected. So people have to look for the prediction of Higgs boson. So nearly for 40 years the search was on, and only in the year 2012, that too on July 4th. July 4th, you know what is the particular significance of that day? July 4th. So that happens to be the Independence Day of USA, American Independence Day, July 4th. So on that day it was announced, they discovered, the scientists at CERN, so they actually very clearly noticed the presence of this Higgs particle in their experiments. Okay? So in the year 2013, the next year, so this was done with the help of one of the most advanced experimental setups in the world, that is called the Large Hadron Collider. So you will hear more about that in the technical session. I think somebody will talk about the Large Hadron Collider, how it is able to generate these particles and so on. So they noticed a particle which was present whenever protons and antiprotons were colliding, they produce all kinds of other particles. So if you notice another particle, it will show up in some kind of a peak. At that particular peak, there will be a lot of masses collected. So they notice a peak around 125 GeV. So what is 1 GeV? 1 GeV is typically the mass of one proton. So this particle, Higgs boson or the God particle, okay, so to say, is present at a mass of 125 GeV, 125 times the mass of the proton. So because of this discovery, once this was discovered, people appreciated the works of Higgs and Englert and so on, and they were awarded the Nobel Prize the next year, 2013. So subsequent experiments and the Large Hadron Collider, till today, several experiments have been done. It is not sufficient if you just want to do one experiment and confirm it. Many other people have to confirm it, only then it becomes science. So that is the specialty of science. Science is very objective. You say something, it has to be verified by other people under same conditions. Only then it becomes a part of science. So it was discovered and people have verified. But still, is it the answer? So once a particular result comes up in science, it generates more and more doubts and questions. So there are more and more questions which are yet to be answered about Higgs particle or the God particle. So there are, for example, either only one Higgs boson is there, many others are there. What is the mechanism which generates the mass of the Higgs particle itself? How is it able to produce its own mass? So there are some questions like that. So does it have any cosmological implications? The cosmology predicts some kind of expanding universe. So this Higgs boson being present everywhere, is it able to produce that kind of a pressure leading to expansion of the galaxy and so on? Okay, earlier I mentioned the standard model. This is all about the Higgs particle and standard model. So there are several questions about it, the standard model itself. So it is not even complete. So physics is always working with theories which are incomplete. Okay? So it always has got both ends. There is always scope for other persons to come in and contribute to science. So that is another important aspect of science. Science is developed by many people working in different places together, and it's a very collective effort, and there are always room for development. It's never complete. Unlike a religious textbook, it is never a closed chapter. It's always an open chapter. So several parameters in the standard model are put in arbitrarily. They have to be taken assumed arbitrarily. And therefore there are questions as to how one is able to introduce these parameters. Is it possible to derive? So scientists are always looking for more and more so-called unification. But you want one theory which can predict everything. So theory of everything. So that is the ultimate goal of scientists. So therefore, if you put in extra parameters and then match the curve, like what you do in experiments, you have some data, you match the curve by some parameters. But how do these parameters come in? That is science. Okay? So people are looking for ways of deriving this parameter, so it is not really that unique. Again, the standard model, by unifying electromagnetic weak interactions, strong interactions, it is not able to introduce universal gravitational force. Gravitational force is there everywhere. You cannot avoid it. So that is not part of the standard model. So how to bring in gravity as part of the standard model is the most important problem in physics, most fundamental, the highest level. And that is called the problem of quantizing gravity. All the other interactions are quantized. So it is believed that gravity should also be quantized. Whether how to do it, how to unify, that is called unification. And if you go to unification means that you go to higher and higher energies, all the interactions look alike. Okay? They just become part of one big sphere. So when you reduce the energy, they separate out. That is what is called unification. Maybe somebody will talk about unified field theory, unification of forces. So that is the thing. So gravity is not yet unified. That is one of the problems, very extreme problems. Now let me move over to the other extreme of very large masses, very large time scales, and very long distances. So this is the field of cosmology and gravitation and astrophysics and so on. So here the important force is the gravitation force. All the other three forces do not contribute. At the large scale, it is gravity which is the dominant thing. Interaction between galaxies, interaction between stars. The gravitational force, that is the contributing force. So by studying, therefore people are studying the motions of stars in the galaxy, clouds in the galaxy, and galaxies themselves in clusters of galaxies. they have come to a very strange conclusion. What is strange conclusion? That in the universe there is a lot of matter which is missing, not known. Okay? You cannot account for the mass that is present. Mass has to be present in order for these bodies to be moving and to be in close proximity to one another. Okay, they should be bound. In order for them to be bound, there must be a lot of matter which is not present in the stars and galaxies. So such a matter is what is called the dark matter. One of the most fundamental problems in astrophysics and cosmology. What is this dark matter made of? It is evidence is there, but we don't know what exactly is dark matter. It is not radiating any energy, but it interacting with other particles, other bodies like stars and galaxies via gravitation. Gravitational force only it has. So how this matter came into existence? How is it distributed in the universe? Okay? How is it going to decay further? So all these are questions which are very important on the large scale. This is what's called the dark matter problem. So along with that, more recently, in the year 1998 or so, people have discovered one more strange thing, that is the acceleration of galaxies. You might have heard of Hubble's law in 1929. Hubble, by studying the motions of the galaxies, came to the conclusion that galaxies are moving apart from one another with a velocity with a proportional to distance. It's called Hubble's law. So 1999 or 1998 or so, the scientists were studying the most distant galaxy. They came to the conclusion that this linear law is not valid. They are moving faster than linearity. So that is called the accelerating universe. So why this is taking place? Why galaxies are moving so much faster, as though there is some kind of repulsive force in the universe trying to pull them away. So that is what is called the accelerating universe. For that also Nobel Prize was given for three scientists in the year, I don't remember the year, 1999 to discover. So this is a problem. People have explained that on the basis of what is called the dark energy. It's even more mysterious than dark matter. Dark matter is lumpy and located in different parts closer to the masses. The dark energy is uniform, spread all over the universe and giving rise to a pressure which is against gravity. So this is expanding the most distant galaxies at a faster rate. What is called dark energy problem. So there are now speculations that dark energy might be coming from the Higgs boson, so-called dark particle, which is there in the nature fluctuating and leading to pressure. Speculation which are not been conclusively proved. Okay. So more recently, of course, coming to the our own galaxy, people have been looking for what are called exoplanets. For that also Nobel Prize are given. So all these discoveries are the most fundamental or most basic type for which Nobel Prizes are given. In the year 1995, the first so-called exoplanet was discovered. That a planet outside our solar system, they are called exoplanets. Okay? By very sensitive instruments. You have a telescope, a very sensitive instrument, you will be able to detect small vibrations or oscillations of the star. So that is one indication that there is a planet around that star. Okay? So such discoveries are now being done. So people are looking for more and more planets. They must be there because Sun is not just a great star in the universe. There are thousands and thousands, maybe 100 billion stars in the galaxy, and at least a billion of them. Sun is a very ordinary type of star. So there must be a lot of planets around these stars. Now there is supposed to be, but the question is, how many are there? How many can have life on them? So this is one of the most fundamental problems, recent trends. Finding planets having life on them. So they look for what are called planets having habitable zone. So for example, in our own solar system, the Sun, the Earth and the Mars, so they are in the habitable zone. It's possible that they have some. So we look for those planets having habitable zone. So these are some of the things that are being done, and investigations are going on around the world in different observatories and labs and so on. More recently, you must have heard about black holes. So another very enigmatic object. Black holes are there, and at the center of every galaxy now they are expecting a supermassive black hole. So how this black hole came into existence? How is it going to evolve? So these are questions being asked. A Nobel Prize was given this year for the discovery of another black hole at the center of our galaxy. Isn't it? It was lady astronomer. What's her name? So she was given the Nobel Prize for, she spent more than 20 years of her life concentrating only on this problem of determining what is there in the center of the galaxy. So by studying the motion of stars around the center of the galaxy, she could identify that there is a very supermassive object. So in the Nobel Prize citation, they don't say black hole. They say supermassive object is there at the center of the galaxy, very compact one, of the order of having 4 million solar masses. The mass of this is 4 million times the mass of the sun. So most of the people assume it is a black hole, but still there is a small element of doubt. It is a black hole or something else. So there are now people speculating black holes are real, if they exist, are really not possible. So these are questions at the highest level. Now let us look at the intermediate mass level. Intermediate mass, which we are familiar with, meters, centimeters, millimeters, micrometers. These are the intermediate, with which we have an access. We have no access in the smallest objects, which are at the Fermi level, or the largest objects. We just have to do experiment and imagine. But these objects we can see with our microscopes, with our other instruments. So these are the intermediate objects. For them, the dominating thing, or the theory, or the quantum mechanics and electromagnetism, these are the only things. The weak interaction doesn't have, strong interaction doesn't come into picture, or gravity. So most of the things that we deal with in normal life, on the intermediate level, are nothing but the objects for which quantum mechanics and electromagnetism can explain most of the properties. So the most important property of quantum mechanics, maybe somebody will talk about those things in this seminar, are the two important properties are what is called the superposition principle of states and the entanglement of states. So these are very highly non-intuitive. We cannot imagine such a thing being existing in the normal world. So these two important properties of quantum mechanical states are responsible for the development of quantum computers, okay, and quantum teleportation. I saw that one of the two other topics, sub-themes in this seminar are quantum computers and quantum teleportation. So while a classical computer makes use of bits that correspond to two distinct states, 0 and 1, quantum computers you have deal with bits and manipulate them, transfer information and do calculation with those bits. The quantum computer is deal with bits which are called qubits, which can take all values from 0 to 1. So the range is very, very large. Okay? So thereby quantum computer can do a lot of calculations very fast, very quickly, simultaneously, parallel processing. So that is the advantage of quantum computers which are being now invented. They are not yet available on the commercial scale. So they are being invented. Okay, but the problem with the quantum computers is that the processors and the other devices, they have to be kept at very extremely low temperatures, nearly close to absolute zero. So otherwise, what is called the coherence between the states, superposition between the states collapses and becomes useless. So there being now one prototype is there at IBM in USA, which is operated nearly 0 degrees Kelvin, and also free from all kinds of other small disturbances, gravitational field fluctuations, electromagnetic fluctuations, small magnetic fluctuations. So they can throw up the quantum state and disrupt the whole thing. So these are things which are being studied, how to make them more robust, okay, reliable, and work at room temperature and so on. In quantum teleportation, another important subject, we make sure of the quantum nature of state. The information is transported from one place to another. Not the body itself is not transported. Information is transported via entangled quantum states. What is called entangled. Maybe somebody will talk to you about that. Quantum states get entangled. So even though you separate them, they remain correlated. Okay, you do something with this state, automatically immediately will have an effect on the other state. That is called entanglement. Even Einstein did not believe in that. Einstein said, how can I believe in such a thing? They're so far apart, You do something in this particular corner and immediately it has an effect on the other part of the system. So he therefore did not agree with this quantum nature of particles, waves and particles. He said there must be something wrong with quantum mechanics. But we now know that this kind of a phenomena of what is called quantum entanglement is really there, and it is very much useful in quantum teleportation and quantum cryptography. So somebody will talk to you about those things. So another important area is superconductivity, which is also mentioned in the seminar. So serious attempts are being done to manufacture superconductors at room temperature. Superconductivity was discovered a long time ago at very low temperature, liquid helium, liquid nitrogen. Now room temperature superconductor, if you are able to manufacture, so that will be a great boon, because you don't lose any energy conducting the current. Okay, all kind of energy transport, current, even information transport can work without heat. So superconductor is very much essential in technology. So, but people don't know how to make them at room temperature. More recently, only last October or so, some scientists in New York, they developed a room temperature superconductor with what are called hydrogen sulfide, some hydrogen sulfide compound. But the only glitch is that it works at very high pressure. Only if you apply pressure of the order of the pressure of the Earth's interior, extremely pressure, only then that material becomes superconductor. So how to manufacture a superconductor room temperature is a big question. If one can do that, definitely you win the Nobel Prize and also become a billionaire. Okay? Because that is the level of technological applications it can have in the world. Okay? So this way, there are so many trends or so many areas which are still open for development and research and discussions and so on, and you are very much welcome to participate in them. And it is a great challenge, not only for you as a career, but a great satisfaction you will derive by being part of such a enterprise where you discover something new and manufacture something new, apply the knowledge. So the developments both in basic science, basic physics, as well as applied physics, which require a lot of technical manpower, and I'm sure seminars and conferences like this will help to prepare the students and the faculty members to take part in such activities. So thank you very much for your time. I hope the seminar will be helpful.